Well, we've gone through an introduction to using the method of initial rates to determine the rate law. So let's use the same data and we'll go and work the problem. Now in this problem, you're told that it's at 1280 degrees Celsius, and then we're supposed to figure out the rate law and the rate constant. Now, the temperature does dictate the rate constant. If you change the temperature of the reaction, you expect the rate constant to change. But for our purposes, since it's being held at a constant temperature, that's a distractor. So let's get rid of it. So let's focus on the rate law first, and then the rate constant. Let's write a general form of it. We don't know the exponents, so we'll write it out as a mathematical equation with variables. So the rate equals the rate constant. We're going to bring the reactants in. And I'm going to raise that concentration to the x power because I don't know what the order is with respect to nitrogen monoxide. And then the other reactant. And I'm going to raise that concentration to the y power because I don't know that one. And that's what we're trying to figure out first, the values for x and y. I did not use the coefficients. The 2's in front of both of those reactants, you ignore those right now. The rate law is determined experimentally. You can't depend upon the coefficients. Now what I need to do is pick two trials. And since I have two reactants, I'm going to pick trials such that one concentration changes and the other one stays constant. By picking trials 1 and 2, concentration of nitrogen monoxide changes, concentration of hydrogen does not change. So that means we're going to figure out x first. Alright, I just shifted things around to make some more room. So we're going to take the rate law for one of the trials and divide it by the rate law for the other trial. So let's start with the left side of the equal sign. And I choose to do the rate for trial 2 divided by the rate for trial 1 only because that's going to give me a number that's at least 1. You can do trial 1 divided by trial 2. It'll work fine. And if you look down below, you see that I left the units out. In this part of the problem, I'm going to leave the units out because they're all going to cancel. X and Y do not have units associated with them. However, when I get to the part where we have to calculate the rate constant, then we have to use units again. Now the right side of the equation. We're doing trial 2 over trial 1. So I'll plug them in, raising them each to the respective x and y powers. And then divide by the information from trial 1. Now remember why we're doing this. Right now, we have a mathematical equation that has 3 variables in it, k, x, and y. We're simplifying this to one variable, one equation, one unknown. You don't know the value of k yet, but it cancels. I don't know the value of y yet, but that part cancels. I'm just shifting things around again to make some room. So that's a little busy. Let's reduce some things down. Looking at the left side, divide that out. Well, that's 4. Now let's look at the right side. We have the numerator raised to the power of x and the denominator raised to the power of x. I don't know what x is, but I can collect terms. This allows me to just now focus on what's inside the parentheses and reduce that down. And that's a 2. So the x is in the exponent, but 2 to the x equals 4. You can do that. What's x? What power is x? Well, x is 2, because 2 squared is 4. So let's see where we are with the rate law. Rate equals the rate constant, and we have the order with respect to nitrogen monoxide. That was x, so that's a 2. And then we have H2, concentration raised to the y. We don't know that yet.